So the first example today on a Taylor polynomial is going to require us first to write a Taylor polynomial and then do a little bit of algebra afterwards. Alright, so example 5 is saying use a third degree Taylor approximation near 0. So near 0 actually throws it into it being a Maclaurin polynomial, but we're going to follow all the same steps. So we need a third degree, so we need up to the third derivative. Our c value is going to equal 0. So we've got f of x is equal to e to the x. So we're taking this basic function, we're getting rid of all the algebra that was done to it. So we're just going to write a Taylor polynomial for f of x equals e to the x. So then we go up to the third derivative, so f prime of x is just equal to e to the x. F double prime of x, still just e to the x. F triple prime of x is e to the x. Since the derivatives are all the same as the original function, that makes our math a little easy. So f of 0 is equal to 1, f prime of 0 is equal to 1, f double prime of 0 is equal to 1, and f triple prime of 0 is equal to 1. So this isn't something that you have to write on your paper every single time, but just for us learning the process, I like to write that out. Alright, so let's write our polynomial. So we know that, so let's remember our definition. We've got f to the n of c times x minus c to the n all over n factorial. Alright, so we know that all of the derivatives are just going to be 1. We know that we're always doing x minus 0, so we're always just going to have just an x in there. So I'm going to do my third degree polynomial. So P3 of x. So f of 0 is 1 plus 1 times x to the first over 1 factorial plus 1 times x to the second over 2 factorial plus 1 times x to the third over 3 factorial, which is 6. So I've multiplied out those factorials because I know that I'm going to have to apply some extra algebra to this. So what I know here is that I'm saying that this represents e to the x. So I'm letting this third degree polynomial represent the function e to the x. Now, I need to make this e to the x look like that function. So the first thing I want to do is subtract 1. So if I subtract 1 here and subtract 1 here, then my new polynomial is just x plus x squared over 2 plus x cubed over 6 is equal to e to the x minus 1. Next thing I want to do is divide everything by 2x. So I'm going to divide this side by 2x. So there's the polynomial, not the polynomial, but the function that I'm looking for. And then I'm going to divide everything over here by 2x as well. And I'm going to simplify as I go. And so what we have here is 1/2 plus, I've got x over 4 plus x squared over 12, which we are saying is equal to e to the x minus 1 over 2x. Alright, so there's our polynomial. Now if we do the math that they're asking us to do, so then it's asking us to find the limit. So if I take the limit as x approaches 0, then I'm going to end up with 1 over 2 plus 0 over 4 plus 0 squared over 12, which is equal to 1/2. Right? So that's the limit of the polynomial that we wrote. Now, if I take the limit of what they gave me originally, so now if I take the limit as x approaches 0 of e to the x minus 1 over 2x, what I end up with is 0 over 0. And so what we actually have to do is L'Hopital's. So I'm going to take the limit as x approaches 0 of e to the x minus 1 is equal to 0. The limit as x approaches 0 of 2x is equal to 0. And so I'm going to say by L'Hopital's, what I know is that the limit as x approaches 0 of e to the x minus 1 over 2x is equal to the limit as x approaches 0, let's get rid of that 0 over 0, of e to the x over 2, which is equal to 1/2. And so you can see that we're getting that same value. And so that's the point of the approximation. And so this one just required a little bit of extra algebra. Example 6 is basically asking us to interpret what a polynomial is telling us and what a graph is telling us. So it says, given that the second degree polynomial is equal to a plus bx plus cx squared, centered about 0. So we're looking here. So this is where x is equal to 0. So that's the spot that we are focused on. What can you say about the signs of a, b, and c if f has the graph pictured at the right? Alright, so let's go through the polynomial itself. Right, so just looking at the polynomial, or a polynomial in general, let's not make that say equals. Let's just say, so a. Alright, so what does a tell us? A is the value we get if we plug 0 in for every x, when x is equal to 0. And if I'm finding when x is equal to 0, what I'm really finding is the y-intercept. Now b, if we think about how we write a Taylor polynomial, b is the first derivative. And the first derivative tells me my slope. Now C, when we're writing the Taylor polynomial, comes from the second derivative. And we know that the second derivative tells us concavity. So now if we take and look at the function that they gave us, so if we look at this graph here, at this point, around 0, first thing I know is that my y-intercept is above the x-axis. I also know that the slope of the tangent line is positive. If I were to draw in a tangent line, I can see that I have a positive slope. And I also know that we are concave down. So using that information, we can determine whether or not A is positive or negative. So based on this, A is above, so I know A is positive, or A is greater than 0. Well, it asks for the sign, so since it's asking for the signs, let's actually talk about positive and negative. So A is positive. That way we're answering the question in the way that they asked. Here it says slope is positive, so what I know is that B is positive. And then from our graph, we are concave down, which means that C is negative.